In this video, we look at a popular machine learning technique called gradient boosting. And gradient boosting is something that's been around since later on in the 20th century, but it's immensely popular today and is almost unbeatable on structured data sets. Now, gradient boosting has a lot of different implementations. What you're seeing here in the pseudocode is just one very specific implementation, but generally speaking, the idea is we want to combine rather a variety of what we call weak learners into a single strong learner. So imagine a decision tree is built and this new green tree builds on the errors that this previous blue tree made, and the red tree builds on the errors that the previous two trees made, and the orange tree then learns from the mistakes that the previous three trees made, and so on. And as we add more weak learners in this sequential fashion, we can drive training error down. But we do need to be careful of, things like overfitting as well. So here's some pseudocode. The way this implementation works is you initialize your initial estimate of f sub 0x, and we're going to set it equal to 0. Now, different implementations have different initializations, but essentially, once we've initialized, we're going to create a total of capital T weak learners. And for each of those individual weak learners, we're going to calculate this quantity called r sub t comma I, and we're going to show that it's nothing but this. As well as that, we're going to also derive this alpha t quantity, which can be shown to be this. And once we've sort of gone through this derivation here, we're going to actually do two things. One, code it up in Python just from scratch. And two, we're going to use a library called LightGBM, which does a very particular implementation of gradient boosting. It is a lot more advanced because it's very recent. It was developed by data scientists and machine learning engineers at Microsoft. But after going through a implementation from scratch and doing LightGBM, hopefully you get an idea of what gradient boosting is doing, essentially. So as you can see here, we want to derive this quantity called r sub t comma I, and it's given by this partial derivative. And what we're essentially doing is we're taking the derivative of some arbitrary loss function L, and that's actually one of the advantages of gradient boosting. It can deal with a variety of loss functions. So we just describe it generally here, but the loss function that we're going to use is squared error, and we're going to multiply it by a half just so that differentiation becomes a bit more convenient, mathematically convenient. And so what we're going to do is we're going to derive this quantity and again show that this is nothing but y sub I minus the output for iteration t minus 1. Okay. And so once we've done that, we're going to use our quantity r sub t comma I, and we're going to define this optimization objective here. Okay. And so what we notice is that this quantity here is given by r sub t comma I, and what we know is that it's given as the negative partial derivative with respect to f of x sub I of this loss function here. So what we can say is this is equal to the negative partial derivative of this loss function with respect to f of x sub I. And what we do is we sum over all j of our indices. And what's going to happen here is that we are going to essentially set every quantity to 0 except for the term in which j is equal to I, but we'll see that a little bit later. So if we substitute what our loss function here is, we know that our loss function is just a half times the actual value minus the predicted value. So what we can do is a half times, well, this is going to be the jth observation, the jth actual observation minus the prediction, so f of x sub j. And because we're dealing with squared error here, we're just going to square this residual, and we're going to evaluate it at the point where f of x sub j is equal to the previous output at x sub j. And this is going to apply to all of our observations from j equals 1 all the way to our nth data point. So what we can say here is f of x sub j is equal to f sub t minus 1 x sub j. And this is going to happen for all j equals 1 to n. J from 1 all the way to n. Okay. And so what we do here is essentially we have to notice that we are dealing with partial differentiation with respect to x sub I. So as I said earlier, we're summing from j equals 1 to n, but we're essentially only interested in the observation index in which j is equal to I. And so what we can essentially do here is say that this is nothing but the negative partial derivative with respect to f of x sub I. And because we're only considering the indice in which j is equal to I, we can say we want to find the derivative of a half times y sub I, because we're considering the index in which j is equal to I, minus f of x sub I all squared. And what we want to do here is we want to sub in the point in which f of x sub I is equal to f sub t minus 1 x sub I, because we're only interested in where index I and j are the same. Okay, and if we do this derivative here, we're going to notice that the 2 comes out the front, and just by chain rule, essentially what we're dealing with here is negative, and we're going to take this partial derivative. So this is going to become the 2 gets transported there, which cancels with the half. And so what we get is y sub I minus f of x sub I to the power of 1 multiplied by the derivative of the inside. So we're going to times by the derivative of the inside, and the derivative of the inside is just -1. And so what that becomes is positive, like that. And so what you're seeing here is that this quantity here is going to be evaluated at the point where f of x sub I is equal to f sub t minus 1 x sub I. And so what we get is this is equal to y sub I minus f of t minus 1 x sub I. And just a reminder, this is your final quantity of r sub t comma I, and this is actually just nothing but a residual. So the residual being the actual value minus the predicted value. Essentially, if you're dealing with like a 2-dimensional case, and you have some points here, and this is what your line predicts, your residual is just your actual minus your predicted. So it's that distance over there. Okay. And sometimes we call this a pseudo residual because depending on the way we define the loss function, it could be a multiple of this quantity. But the way we've defined it here by this half out the front, it's actually made it very mathematically convenient. So that's just a residual. Okay. Cool. And so our optimization objective then, we can sub in this r sub t comma I point that we just found. And so what we can say is that if we write down the expression for the optimization objective in this GB3 section of the code here, what we can say now is that h sub t is equal to the argmin. So what we do is for each of these individual t iterations, we look at fitting a model to our new data set D, which comprises of our features as well as our sort of modified response, which is actually going to be this r sub t comma I quantity. And what happens is we fit a model D to this new data set. So essentially, instead of the dependent variable being y, it's actually going to be this new quantity r sub t comma I. So we're fitting a decision tree most of the time. It can be something else, but most of the time it's a decision tree of depth, not that much, maybe depth 1 or depth 2 decision tree. And what we do is we fit that decision tree to this modified data set. And so as more formal notation, it looks a bit like this. So we take the argument f, an element of capital F being like the set of all base learners. And what we do is we take the sum from I equals 1 to n, so all of our n data points, And this loss function, r sub t comma I, what we can define it to be is nothing but this. So we have a half, and we take the actual minus the predicted. So what we're dealing with here is r sub t comma I goes in the place of y. So what we can do is just simply write y sub I minus f sub t minus 1 x sub I minus the prediction, which is f of x sub I, and square the difference. And so once we've calculated r sub t comma I and created a new data set where the dependent variable is r sub t comma I, and once we fit most of the time it's a decision tree to this new data set, what we now do is pick a learning rate. Now, this is the same learning rate that you're talking about with other machine learning algorithms. It just controls the speed in which we reach our global optima. But what we can do is either pick a fixed learning rate, so maybe something like 0.01 or 0.1, something that you could tune. But what we're going to do is we're going to set an adaptive learning rate. So what's happening here is that at every iteration t, the learning rate is going to be different, and it will be decided by the answer to this optimization objective. So it's going to be, we're going to set this alpha t to whichever value of alpha can minimize this quantity here. And just from before, we're going to show that that is nothing but this quantity here, okay? Okay, so essentially we're showing that. And if we just go from scratch here, we can say that alpha t is equal to the argmin, so the value of alpha that minimizes this loss function. So we can take the sum from I equals 1 to n of, now our loss function was just a half times y minus y hat. So L y hat is equal to, that was our loss function. And now in the space of y is just going to be y sub I. So this is going to be a half times y sub I minus, this is going to be your y hat. So minus the prediction here, which is f sub t minus 1 x sub I plus alpha times this h sub t, which we looked at earlier, h sub t x sub I. And as per our loss function, we have to square the residual. And so what we're going to do is we're going to do exactly that. So hopefully I haven't missed a bracket there, but we're going to square the residual just like that. Okay. All right, so this is what we're dealing with. You can also say that this is the argmin over alpha of this summation. So we can make a little adjustment to the summation. This is just a half times y sub I, and expanding the brackets, we get minus f sub t minus 1 x sub I minus alpha h sub t x sub I all squared. Okay. And in finding this optimal alpha, we have to set the partial derivative equal to 0, the partial derivative with respect to alpha equal to 0, and solve for that alpha. And so what we're going to do is I'm just going to define this quantity as maybe capital L. So I'm just going to write that capital L is the sum from I equals 1 to n of a half times, y sub I minus all of this. So minus f sub t minus 1, x sub I minus alpha h sub t, x sub I, and square that residual, and square this difference between your yi and what's acting as your y hat I over here. Okay. So we can take this partial derivative with respect to alpha, and so del L on del alpha is, again, the 2 comes out the front and cancels with the half, so very convenient. This becomes the sum from I equals 1 to n of y sub I minus f sub t minus 1 x sub I minus alpha h sub t x sub I minus 1 from the power, and times by the derivative, the partial derivative, with respect to alpha. And so what we get here is times by negative h sub t x sub I. Okay. And what we're going to do is we're going to set that equal to 0 for stationary points. Now, it will be a minimum, but what we can do is set that equal to 0 for stationary points. Now, if we set this equal to 0 and solve, what I can do is I can times both sides by -1. And so what we get is the sum from I equals 1 to n of y sub I, and I'm going to multiply everything by this h sub t x sub I. I'm essentially just multiplying to get h sub t x sub I minus f sub t minus 1 x sub I h t x sub I minus alpha times ht xi all squared. Okay. And what we're going to do is set that equal to 0. All right. Now what I'm going to do is I'm actually just going to break up the summation. And the reason why I'm going to break up the summation is that so we can get one term here, and then we're going to have a particular term that has the alpha in it that we want. So what we can say is that this implies that the, I'll just move it over here. So the sum from I equals 1 to n of y sub I minus ht x sub I, sorry, not minus, times, ht x sub I minus the sum from I equals 1 to n, again, just summing each term individually, f sub t minus 1 x sub I ht x sub I minus the sum from all of this, right? So, and in fact, what I'm actually going to do is I'm going to, oh, you know what, let's just do it. So minus the sum from I equals 1 to n of alpha times h sub t x sub I all squared, and we're going to set that equal to 0. We can move this term to the other side very simply by just doing a small rearranging. So what we can do is rewrite this whole thing. So h sub t sub I equals, now this part here is just, we can take the alpha out. So what we get is alpha times the sum from I equals 1 to n of h sub t x sub I all squared. All I've done, just move that term to the other side. And what we can get by doing this is by just dividing by everything that's not alpha. So what we're going to get is alpha is equal to this whole thing. So I'm actually going to put it back in one summation. So we get the sum from I equals 1 to n of this whole thing. So y sub I h sub t x sub I minus f sub t minus 1 x sub I h sub t x sub I. And we're going to divide by everything that's not alpha. And so what you get here is this. The sum from I equals 1 to n of h sub t x sub I all squared. And let me just move it over here just to create some space. What we can now do is we can notice that to follow this form, we have to take the h sub t x sub I out. And so we get alpha is equal to the sum from I equals 1 to n. And we notice that h sub t x sub I is in both terms. So it's very easy to factorize. We just get h sub t x sub I multiplied by yi minus f sub t minus 1 xi. Cool. That. And what we can do now is leave the bottom as it is. And you'll notice here that this becomes what we were trying to derive over there. Great. Okay. And that is your alpha t, we've just done it in adaptive fashion. And what you do now is that your prediction at your tth iteration is given by the t minus 1th iteration prediction plus alpha times the output to your optimization here. And you keep doing this from t equals 1 to capital T. And once you've created t of these, capital T of these weak learners, your final prediction for your model for a particular observation is given by f sub t. So your prediction at iteration capital T. So that's it. We'll now look at implementing this in some code in Python. It won't be too hard because we've already got closed form solutions for our learning rate and for our r sub t comma I quantity. But once we do that and look at the code section, we'll actually do a much simpler implementation using LightGBM, which does a lot of the heavy stuff for us. In fact, it does pretty much all of it for us. So stick around and I'll see you guys in that part. Okay, so here we're going to implement a gradient booster, just a very simple one in Python using nothing but pandas, numpy, matplotlib, and we will use this decision tree regressor class from scikit-learn, but you can do it from scratch if you want to. I just think scikit-learn has a really nice implementation of it. And so in creating h sub t, eventually, it's going to be a useful thing for us to use. But the rest of it will be from scratch. So in building this model, we can create this class, which I've just called gradient boosting regressor. You can call it anything. And when you create an object of this gradient boosting regressor class, we can give it three things. One being the number of estimators, so essentially capital T. The next being max depth, so how deep you want each individual weak learner decision tree to be. And the learning rate, which we saw from before, can be either fixed as a constant alpha or chosen adaptively depending on which iteration T you're in. Okay. Cool. And we're going to store those all as attributes. Okay. We now have the fit method, which essentially fits our gradient boosting regressor, which fits our model, which fits our model to the training data. And what we're doing here is creating this data frame called predictions. You don't have to do this, but it is really nice to work with pandas data frames. So we're going to add things to this predictions data frame eventually, but let's just create an empty one to start off with. Now, f sub 0 of x equals 0 is our initial prediction. And so what we can say is we can use numpy vectorization essentially to create n amount of zeros. So we can create a n-dimensional zero vector using numpy, and we'll store this in a variable called f sub 0. Okay. Now, you'll notice that because we want to start building capital T decision trees, weak learners in our case, we want to start at t equals 1. And so if we look here, f sub t minus 1 is going to be f sub 1 minus 1, which is going to be f sub 0. So that's just a little adjustment that you can make there when coding this. And so what we do is I've just created a variable capital T, which stores the number of trees the user wants to build. And so what we can say is that for t from 1 to t, so in other words, for t in range 1 to t plus 1, because we know range in Python snips off the last value, so we can just move to the last one, to the one after that, sorry. And so in this little II stage, we have to look at what GB1 asks for, which is r sub ti. And we know that r sub ti is nothing but yi minus your prediction at iteration t minus 1. Okay. And if we are at our first weak learner, if we are building our first weak learner, what's happening here is that t is equal to 1. And so what our r sub ti quantity is y sub I minus f sub 1 minus 1 xi. And so that is just f sub 0. And if t equals 1, that's what we're going to store rti as. And keep in mind, this shouldn't really be called RTI because we are doing it to an entire vector. So we are using vectorization in NumPy, but it is happening to each of your observations I. And in the case where T is between 2 and capital T, we can just simply use this formula. And you'll see how this all sort of plays out. Okay. Now, you'll notice here that with GB2, we have to create a new pseudo data set called D sub T. And D sub T has your X variables just like before, but your Y variable is now that residual column that you create, R sub Ti. And in doing so, we're going to create this data set, which we already have, right? Because we have our X, which we pass in as a two-dimensional array, and we have R sub Ti, which is our one-dimensional vector that acts as our like Y variable in our pseudo data set. Okay. And so with GB3, we fit a model to D sub T. So we fit a model to the training data, the pseudo training data, and in doing so, we're going to use the decision tree regressor class from scikit-learn, setting it, configuring it with a max depth equal to whatever we pass in as the max depth. And again, we're going to fit it to the pseudo dataset D, which contains X, and our Y variable this time is R sub Ti. So we're building a decision tree where the dependent variable is your R sub Ti. Okay. And we know from GB4 that we can set the learning rate either 1 as a constant fixed or 2 in adaptive fashion. So if we set the learning rate to be adaptive, so if the user puts in the string adaptive, what we know from before is that the numerator can be given as this over here. So all I've done is I've taken H sub T, right? Because we're making predictions on each of our I observations, and we're timesing that by Y minus F sub T minus 1 X sub I. And again, we're doing this operation to an entire array, and then we're taking the sum afterwards. And it's mimicking what you're seeing on the screen here. Now the denominator is just, that is squared. Sorry, that's squared. You'll see here that if you rewind earlier on in this video, you'll see that it is in fact squared. I just forgot to patch it up, but I've done it now. And what you'll see is that the denominator, that's what it looks like in code, and that's what it looks like on paper. And so our adaptive learning rate, alpha T, is just going to be the numerator over the denominator. And in the case where we want a constant learning rate, so let's say the user puts in 0.1, all that we do is we just store that in a variable called alpha. Okay. And so GB5 requires us to implement this step over here. So F sub Tx is equal to F sub T minus 1x plus alpha T H sub Tx. And so it might not immediately be obvious what F sub T minus 1x is, because we have alpha T and we have H sub Tx, but it might not immediately be obvious what this is. And you'll see that just by rearranging this formula here, you'll see that if we make F sub T minus 1 xi the subject, you get yi minus r sub Ti. And there we go. And so that's what we can store as F sub T minus 1. And we're going to implement our update rule where we set the prediction for our current iteration lowercase t, and we're going to set it equal to the previous iteration plus some learning rate which changes depending on the iteration, or not if you choose SS1. And we're going to times that by the output of our weak learner, which in our case is a decision tree, with a max depth equal to whatever we set the max depth to. Okay. Once we've run through all capital T iterations, we're going to store the final prediction in F sub capital T. So by the time we exit this for loop, this will be f sub capital T, which I'm just going to store formally just to, show the similarities between the pseudocode and the actual code. Now, this is not important. This is just for visualization purposes so that we can plot the model. I've just stored it in a data frame, creating a new column equal to this f sub capital T vector, which is our final predictions. And I'm just plotting the actual data with what our model predicts on that same data. And so let me run that. And what you'll see here is that we can just generate some data. You don't actually have to worry about this code, but this code's just going to generate some data. And you'll notice here that I've just converted X to a 2D array because our class, at least the way I've implemented it, ensures that X is two-dimensional, okay? And so if I run this and we generate data that is a 2D array and a 1D array, we can generate some data. And if I run this, I can call my gradient boosting regressor class that I've created. And we know that it takes in 3 arguments: the number of estimators to build, the maximum depth, and the learning rate. And so what we're doing is we're just setting that ourselves. So let's say we want to build T equals 10. So we want to build 10 weak learners. We want each weak learner to be a depth 2 decision tree. And we want the learning rate to be maybe, I don't know, 0.1. And if I fit this model to the training data, it's going to calculate the values that our gradient booster predicts. And as well as that, it's going to create a little plot. And so if I run that, what you're going to notice is that because of this constant learning rate, and because of the fact that we've only built 10 weak learners, our algorithm needs a little bit more time to almost warm up. So let's say I increase this to 100 estimators, and now you're going to see it's captured the trend in the data. It's captured the patterns in the data a little bit more. And with all of these 100 iterations, it's created a reasonable fit to the training data, maybe a little bit overfit, but there's your fit. Now, let's say I set this to adaptive and I allow the max depth of this tree to be 1. And you can just, essentially you could just run a for loop, but let's just try different values and just see how things change. And so you'll notice that if these learners are individually too strong, so we don't have weak learners that sequentially build up to create a strong learner, if we create a weak learner, or if we create a H sub T that's too intricate, what you're going to see that if I set the max depth to something a little bit higher, it's going to essentially interpolate the data. And this is, of course, a highly overfit model. And, there's just a balance between tweaking these parameters in practice, like n estimators and max depth, to ensure that you have something that is, a good balance that, adheres to the bias variance trade-off. And so that we don't overly underfit or overfit to the data. Okay. And so again, you could run a for loop. You could maybe run an inner for loop that looks at constant versus adaptive. And then you could look at how n estimators changes and see what changes in max depth does. But essentially you can just experiment with some values here. So let's say I build 50 trees, each with a max depth of 1 with an adaptive learning rate. And if I set this to constant, you'll see that the fit changes. Sorry, not constant. We actually want to set it to a constant of 0.1. Or let's say I change this learning rate to something that learns a little bit quicker. We get that. And so I encourage you to just experiment with different n estimators, different max depths, and different learning rates, both constant and adaptive. And you'll see how the fit to the training data increases. No, that doesn't make sense. You'll see how things change as you tweak these hyperparameters. Okay. So in the next part, we're going to look at LightGBM, which is just a very like high level implementation. You don't really actually have to understand what a gradient booster is to be able to use it. But you'll see that you never have to do this in practice. This is just one particular implementation. In practice, it's just going to be like a model.fit sort of thing where you might have to tune some hyperparameters as well, but it's nowhere near as complicated as something that you have to sort of do manually. Okay, so in this last section, we're going to look at a gradient booster using an existing package. So you'll see here that we're going to be using something called LightGBM, in particular, the LGBM regressor class, because we're building a regression model. And so all I've done here is just created a fake data set with 1,000 rows and 10 X variables, so 10 predictors. And what you'll see here is a really simple data set. There's nothing really to it, just a clean data set with no missing values, nothing like that. So what we want to do ultimately is build a model using our X data to try and predict our Y variable, okay? More than that, though, we actually want a model that can perform well on unseen testing data. So essentially, we want our model to do well on data that it's never seen before, okay? And so what I've done here is I've just created my matrix X and my response vector Y. And what we want to do here is, again, use our X's to predict Y. So I'm just splitting them up. And because we want to build our model using training data and evaluate our model using testing data, what we can do is just split it up into 75% training and 25% of the observations will go to testing. And all I've done here is I've just set this random state equal to 1 here. You can set it to any integer, but it's just so that when I run this notebook again, you get the same results. It's just for consistency. Okay. And so what we want to do now is fit a model to the training data. So what we can say is maybe model is equal to LGBM regressor. And all that we do here is we just fit it to the training data. So we can dot fit, and we fit that to X train and Y train. Now, this should be very quick to train because LightGBM is very fast. And so in less than a second, we fit this gradient booster. And for those who are familiar with R squared, we can get the R squared of this model just by simply doing model.score. So if I do model.score and I want to see the score on the unseen testing data, what I can do is just simply pass in X test and Y test, and we get the R squared of 0.92 essentially. Okay. Now, what you'll notice is that if I hover my mouse over this part, you'll see that these are all the default arguments that you can place in. And the question is, what happens if 0.01 wasn't actually an optimal learning rate, or the number of trees to build of 100 wasn't actually the best option in increasing this R squared, if that's what we were going for? So what we could do essentially is tune a whole lot of values. So we can try different values for N estimators, try different values for learning rates. There are so many things that you can tune. You can tune the max depth as well of each of your trees. And then you have all of these more complicated arguments that you can adjust, such as regularization, which you'll see in things like ridge, lasso, and elastic net regression. And so what we can do here is set up some parameters that we want to tune. And the way you do this is by setting up a dictionary. And let's say I want to tune the number of estimators. It's by default 100, but let's just see what happens if I try 100, 150, and 200. And depending on how much time you have, you can specify a whole lot of values. And so let's go max depth, and let's see what happens as we increase the depth. So let's say I want to go from 1 to 10, for example. So using NumPy, we can go from 1 to 10, incrementing by 1. And just because of the way range works, this is actually going to be 11 because it chops off that 11 value and finishes at 10. Okay. Another thing that we can do is we can adjust the learning rate, which I believe was defined as learning underscore rate. So what we can do is we can say learning underscore rate, and let's just see what happens if we try 0.1 and maybe 0.15, as well as 0.2. Okay. So we can try that. And I think, yeah, let's just leave it at that. And so what I'm going to do now is I'm going to create this new model, the one that we want to tune. So just like before, it's going to be this LGBM regressor, but we're not going to fit it just yet. We're just going to set it up. And so what we can do now is perform something called a grid search, where we search over all possible combos that we've specified. So for example, when n estimated is 100, max depth is equal to 1, learning rate is equal to 0.1, build a whole lot of LGBM regressor models, and using cross-validation, get the cross-validated accuracy metric that we're after. We'll use R-squared. And so what we can do is we can say something like this. I'll define a variable called search, and we're going to create an object of this grid search CV class. And what this essentially means is that I want to perform cross-validation and search this entire grid of parameters in doing so. And so the first thing that goes in there is the estimator, which is our new model. The second thing is the parameters that we wish to tune. And then we can pass in some other things like, let's say we want to do 5-fold cross-validation. And in doing so, we want to assess the performance of each model on R-squared. So we can say scoring is equal to R2. And what we can say is, yeah, we can just probably leave it there, right? If you want some detailed output, we can just set the verbosity equal to a higher number. So let's just go 2. Okay. And so if I run this and I fit this search to the training data, it's going to explore all the possible combinations that I've specified here. And so as I let that run, you'll see here that it's testing a whole lot of different combinations. So learning rate equals 0.1, max depth is 4, and estimated is equal to these changing values. And so as you specify more parameters to tune and you specify more values within each of those parameters, just keep in mind that grid search CV is going to take quite a lot of time. What you can do as an alternative is explore something called randomized search CV, where it's only going to explore a particular specified amount of combos instead of all of them. But we've just used grid search because it only really took 32 seconds. Okay. And so once we've fit this search, we can extract some attributes that might be useful to us. So the first thing that we can do is get the best parameter combo, and we can do that by using best underscore params followed by an underscore. And basically what this is saying is that when the learning rate was set to 0.2 and the max depth was 1 and the number of trees to build was 200, based off cross-validation, that returned the best average R-squared, okay? And so what we can now do is we can store this final model that has all of these parameters set up in a variable called final model. And let's just say that final model is going to be search.bestEstimator. And best estimator stores our model that has all of these parameters set up. Okay. And we don't need to refit it because it already comes to us refit. So I wouldn't have to go final model.fit xtrain, ytrain. Straight away now we can get the score of this final model. And so what we can do is simply just do this. So what we want to do now is get our result on the unseen testing data. And what you'll notice here is that the R-squared has gone up to 0.97. So in other words, tuning our model was a beneficial thing to do if increasing R-squared was our goal. Now, of course, R-squared has its disadvantages, which we won't go into. But if the objective was to increase our R-squared metric, tuning the model seemed like a good thing to do. Okay. Another thing that we can do is look at the importance of each of your features. So potentially LightGBM believes that maybe X3 was more important than X4, which was less important than X5 or something like that. So what we can do is using the LightGBM module, we can do this. So I believe it's a plot. I think I might have to just go dir LightGBM. And this will tell me all the methods that I can use. So it's plot importance. Here we go. So if we do LightGBM dot plot importance, and we plot the importance of our final model, what we're going to see here is that hopefully if that works, yeah, there we go. It's basically ranking our features in terms of importance. And we're not going to go into how this feature importance score is calculated, but essentially, according to LightGBM, the model believes that X4 is the most, in quotes, important variable, followed by X10, followed by X6 and X7, and so on. Yeah, so another thing that we could do, you don't have to do this, but you could actually, like, just if you were curious, for example, you could just look at the actual values versus the predicted values and actually just like look at the raw values themselves. So what I can do is I can create a data frame called results, and I'm going to set this as a pandas data frame, and PD is just pandas, which I've imported as PD. And so we can use the data frame class in pandas to basically set up a data frame that has our actual values and our predicted values. So let's just call this actual, and that's going to be nothing but Y test, the actual testing data, and then the predictions are going to be nothing but your final model. And we want to make a prediction based off our testing data, and this is going to give us our predictions for Y. Okay. And if I just take a look at like results, let's just look at maybe 10 random rows of data. And what you'll see here is just some of the comparisons. So basically, this is what the actual value was, and this is what our final model predicted. And you see, they end up being relatively close to each other, characterized by the R-squared, which was quite high, or very high. And so, yeah, of course, there's much more things that there are many more things that you can do with this LightGBM model, but you can fit it with the default parameters, which typically performs pretty well, or you can decide to tune it if you feel like you have some time and want to explore different values of different parameters. Now, keep in mind, there are so many other ones that you can tune as well. So we just tuned these 3 parameters, hyperparameters, but there are plenty more that you can tune. And so that's pretty much it. And we'll see you in the next one.